Before I start, I would like to thank Professor Elighausen for his contributions. Okay, so this presentation was part of my PhD, a small part of it, regarding the coefficient alpha setup in high-strength concrete. So just a small overview. As we all know, bonded anchors or adhesive anchors are widely used in construction. So here we have a small example of an elevator test tower in Rottweil in the vicinity of Stuttgart, where the membrane facade is anchored to the concrete walls using adhesive anchors. So in this case, the adhesive anchor, of course, is so the load is transmitted to concrete using using a chemical interlock. And of course, nowadays what we use mostly for the bond strength is the uniform bond model to describe it. So the presentation today is going to be divided into three main parts. So first of all, a small introduction, continued by testing procedure, and at the end, the results will be shown. So the question arises, what is the coefficient alpha setup? So mostly there are two methods to test bonded anchors. So first of all, we have unconfined setup. So it's shown in this case. We have the confinement. The support diameter in this case is larger than 4 times the diameter, the embedment depth of the anchor. And afterwards, we also have the confined test setup, where the diameter is supposed to be, of the support diameter is supposed to be 1.5 till 2 times the diameter of the drill bit. So both of these values for the support diameters are according to the current guidelines, EAD or the ACI. The ratio between the bond strength of the unconfined test to the bond strength of the confined test gives us the coefficient alpha setup. So if we look at this figure here, we have the embedment depth over load. We have 3 different failure modes which are mostly common for adhesive anchors. So first of all, we have steel failure, we have concrete failure, which is the gray line, and lastly we have also pull-out failure, which is most common when we test in confined setup. So the small little area here represents the embedment depth which we would have to test in order to get our alpha setup value, because in reality this value is very small, or this area is very small. We cannot perform tests for alpha setups. That's why we perform confined and unconfined tests. So starting from testing procedure and the parameters which were observed. So first of all the tests were performed in high-strength concrete, C90-105, with a compressive strength of 85 to 115 megapascal. 2 different steel components were used in the test, M12 threaded rods and D12 reinforcing bars. And only one adhesive anchor was used, and this is epoxy resin with a hardening time of approximately 24 hours. However, all the tests were performed later, up to 1 week later. The parameters which were varied were, first of all, the embedment depth. So we have 4D and 8D. We have the support diameter. It was between 0.24 H effective to 2 times H effective. And lastly, we have the bond length, 0 to 100%. So what does bond length mean? So in the figure here, you see the first one. We have the reference test, where the H effective and bond length are the same. So we have 100% bond length is our embedment depth. Secondly, there were configurations A and B. In this case, for configurations A and B, we had 50% bond length. However, 2 different methods were used to test them. So for configuration A, we have the first quarter was debonded, and afterwards we have bonded for the second quarter, and so on. Whereas for configuration B, the first 50% was debonded, and then the second 50% was bonded. As the bonding mechanism was used measuring tape. Afterwards, we had configuration C. In this case, only the lower quarter of the embedment depth was bonded. And lastly, configuration D was used only to see if there was friction in the borehole when testing. So here are the two different test setup which were used. So on the left one, we have the test setup for a confined test, and here for unconfined. As you see here below, we have the small confinement, and here we have this D, which is larger, 2-4 times H effective. So now if you go to the results, so first of all, the first parameters I mentioned was the embedment depth. So here we have the results for M12. In this case, all the results show also the different failure modes which occurred during the test. So if we see for confined setup, we have an increase of the failure load up to an embedment depth of 70. Afterwards, a slight decrease in the load was observed. And also the failure mode transforms throughout the tests from mostly a mixture of pull-out and pull-out with mortar to pull-out failure, and at the end here at 8D we had also steel failure. I forgot to mention before, for all the tests with 8D, the steel elements were hardened in order to avoid steel failure. However, that was not possible because the concrete strength was also very high. So similar results we see for unconfined. So in this case, up to 6D we have a very large increase of the failure mode, and from 6D to 8D we have an increase, whereas for the confined we saw that from 7D to 8D there was no increase. Now going to the test results with the reinforcing bars. So in this case, only three embedment depths were tested for D6D and 8D. We see an increase of, for both confined and unconfined, we see an increase of the failure load up to 6D. Afterwards, similar to the M12 test, the confined test showed almost no increase in failure load, whereas for the unconfined we have an increase in failure loads. And of course, the transition of failure modes is observed for the reinforcing bar as well. The next parameter studied was support diameter. So first of all, we have M12. In this case, only two diameters were studied. It was the standard ones, which mean 1.5 to 2 times diameter of the drill bit for confined, and then larger diameters for larger than 4 times H effective for unconfined test setup. So if you see here, we have on the x-axis, we have the diameter, support diameter, and on the y-axis, we have the ratio between the bond strength and the bond strength only for the failure mode pull-out within the same series. So you can see here that this ratio is a mean value at approximately 1. If we increase the support diameter, as is to be expected, we have an increase of, we have a decrease of the ratio, which also, as you can see here, we have a larger scatter of the results. So for 300 millimeters, this scatter is quite high compared to 440 millimeters, even though both of them are considered as unconfined test setup. And also, the relative value is also a bit higher for 440 compared to 400 millimeters. So for the support diameter, for the reinforcing bar D12, in this case, more diameters were studied. So we start at the beginning with 14.4 millimeters, which is 0.24 times the H effective. In this case, this is lower than the accepted value from the acceptance criteria now, and you can see that we have a higher ratio, or almost 1, between the bond strength and the bond strength for failure mode pull-out. If we go to the standard used support diameter, we have almost 1, so it is to be expected. And then with an increase of the diameter up to 120, we see the reduction in failure load exactly, and then we can say that for D12 as well as for M12, we have a curious behavior for unconfined tests. So as you can see here, we have a larger scatter at 300 millimeters and smaller scatter and higher ratio for 440 millimeters. So now we go to the test with bond length. So in this case, on the left, we have the test with confined M12. For bond length, only 3 different embedment depths were tested, 4D, 6D, and 8D, starting at approximately 48 millimeters. These results here, in both cases, represent the reference test. So if you remember, the reference tests were the tests where the bond length and the embedment depth are equal. And all the other results below 48 millimeters are the results from the partially bonded anchors. So in this case, at the beginning here, we have all the results with configuration D, where only friction was observed at approximately 1 kilonewton. Afterwards, the test with configuration C, we have in this area, and they mostly exhibited pull-out failure. Afterwards, in this large area of points here, we have the results from configuration A and from configuration B. So here below you can see both configurations. They are, the interesting part in this test was that for the confined test setup, configuration A had higher failure loads compared to configuration B, whereas for the tests in unconfined, it was the opposite. So configuration B was better, had better values than configuration A. And as you see here, with an increase of the bond length, we also have more higher mixture of pull-out and pull-out in mortar failure compared to the configuration C. And similar, we can see for unconfined tests. So in this case, we have mostly concrete cone and pull-out failure. So now if we see the previous results in another diagram, so in this case we have on the y-axis the ratio between tau unconfined and tau confined. This would be our alpha setup. And on the x-axis we have tau confined to tau max, where tau max is the concrete, it is the bond strength needed to activate the concrete. So in this case, 3 different data sets are shown. We have the black ones, the black squares. These are the tests with fully bonded M12 anchors. We have the blue dots. These are the tests with D12 reinforcing bars, and everything which is green is the test with the partially bonded anchors. To evaluate our alpha setup, only the tests with fully bonded anchors are considered. So in this case, you see that the values vary from 0.5 to 1, and on average, the value was 0.75. So this indicates that the current value which is used for standard diameters and standard embedment depths in the current guidelines is accurate and conservative. So now we come to the last part. We have the results. So we have, first of all, for the embedment depth, as we saw, we had an increase of the failure mode up to 6D for the reinforcing bar, D12, and up to 7D for the threaded rods. However, for the confined test, we saw a decrease in the failure load afterwards. The test with support diameter showed an increase. Showed a decrease in failure load with an increase of the support diameter, as is to be expected, and the failure modes for transition mostly from 100% pull-out failure to a mixture of pull-out failure and concrete cone. And the test with bond length, as I mentioned before, configuration A had higher failure loads for confined test setup, whereas configuration B showed for unconfined test setup. And lastly, the configuration C exhibited 75% lower failure loads compared to the fully bonded anchors. and the unconfined test showed a 65% reduction. So lastly, the alpha setup factor varied between 0.57 to 0.92, and an overall value of alpha setup of 0.75 is generally considered sufficient for ensuring the reliable anchor performance in unconfined testing. So thank you very much. Do you have any questions?